Okay, so we're still on momentum today. Last time we did P equals mv. We did a delta P equals m delta v. We did delta P equals F delta T, which that's also known as impulse here. And then we also said M delta V equals F delta T. And of course we realized that delta V equals VF minus VI. And we used predominantly, well, I guess we used them all. We used all these formulas to solve some problems, and I think most people ended up being pretty good at it. You just have to be careful with your signs and all that sort of thing. So this wasn't really that bad. Today, we're going to talk about the momentum of more than one object. And so I'm going to start with a very general example. Okay, imagine that we have two balls. We'll call this one A, and we'll call this one B. And each of these has a different momentum. So we'll say this has P, momentum P sub A, and this one has momentum P sub B. Maybe this one has more momentum than the other. And let's say they're balls of equal mass for now. So let's come over here and say M sub A equals M sub B. They're identical balls with equal mass. This one has more momentum than this one. So that's less momentum. Okay. What happens since this has more momentum? Since they have the same mass, this one must be going faster. So what's going to happen is, after some period of time, this one's going to catch up, and they're going to hit each other. And you have A and B, and there's going to be a moment of impact. That's the impact. So at that moment of impact, it lasts a period of time, not a very long period of time, so there's some time t where these are in contact, and when they hit each other, then we get a force. So some force is going to be applied, and Newton's laws tell us that there's going to be a positive force this way, and then a negative force, or a force in the other direction, the other way. That makes sense? So, well, force and time, that sounds a lot like impulse. So this ball is going to receive an impulse that is negative F delta T. This one is going to receive an impulse that is positive F delta T. So after that happens, depending on the velocities and a few other things, our first ball, maybe it would go back the other way because there's a force acting against it, and our second one has more momentum here. So now we have a new momentum. We'll call it P prime sub A and P prime sub B. That just means the new momentum. So here's our toy scenario where we have a ball with more momentum than the other one. They're identical. They hit, they bounce off. One goes backwards, the other goes forwards, but faster than it was going. Okay. What has to be true here is that the overall momentum has to be the same. And by that I mean, I didn't do a great job of illustrating that here, that the amount of momentum that was lost by A is the amount of momentum that was gained by B. The momentum can't go away in a perfect system like this. Now, real world, there are things like friction and heat, and so you have energy loss that way. But in our toy example, there's the overall momentum does not change. And that idea is called conservation of momentum. And the law of conservation of momentum states, the momentum of any closed isolated system does not change. What do we mean by closed isolated system? That means some ideal circumstance, like I mentioned earlier, where there's not going to be energy loss from friction, where we've got some small number of objects that only act on each other and there's no outside forces or outside actors or anything like that. Our problems that we're going to look at are going to be like two cars or two balls or two train carts or something like that. So let's revisit our example with our two different balls. Imagine that this is ball A and this is ball B, and let's say let's just say we know some information about them this time. Maybe they both have the same mass, so the mass of A equals the mass of B equals maybe 3 kilograms. Alright? And let's say that B is not moving. So the velocity of B is 0. And maybe A is moving. Maybe A has a velocity, I don't know, 3 meters per second. Okay? So this ball is moving towards this ball, and that ball is sitting still. Okay? Let's say that they hit each other, and that then after they hit each other, now A is going backwards. We'll call this VA prime, saying that it's the velocity after the impact. Maybe it's going backwards at 1 meter per second, so better make it negative. So we'll say our VA prime is negative 1. Let me make that a little neater. Negative 1 meter per second. Well, if A is going backwards at negative 1 meter per second, then B must be doing something because our momentum can't change. Our overall momentum can't change. So what we can do is we can figure out how fast and in what direction B would now be moving. If we know this velocity after impact, we can figure out this velocity after impact. How can we do it? Well, let me make some space. Okay. Well, we're going to use this fundamental equation. The equation says that momentum of A plus momentum of B equals momentum of A plus momentum of B. Now notice that these are P primes. That means that these are the momentums after an impact. These are like, sort of think about this as initial and final momentum. This is the momentum after the change. Notice that the sum has to stay the same. Now you may say, okay, why are we talking about momentums? We've been talking about velocities. Well, don't forget that momentum is just mass times velocity. So really what we can do is we can do this. We can say MA times VA. Let me clean that up. MA times VA plus MV times MB. Man, it's not my day. MB times VB is going to equal, well, P prime A, well, that's going to equal V prime A times MA plus V prime B times MB. Now that may look scary, but it's not bad. Just we know the momentums, the sum of the momentums before the impact has to be the same as the sum of the momentums after the impact. And we know that momentum is mass times velocity, so I just plugged all that in. Just made that, it looks a little intimidating, but it's not. It's just keep your numbers straight and you'll be fine. So we know all of this, we just don't know velocity of B prime. That's what we're looking for. So let's solve for velocity of V prime, velocity of B prime, excuse me. Let's clean this up a little bit. Let's actually, I'm going to break my own rule and plug the numbers in first, just because this is ugly. Well, MA times VA, well, our velocity of A at the beginning is 3. Our mass was 3, so that sum is 9, plus mass of B times velocity of B. Well, velocity of B was 0, so B had no momentum before the impact. After the impact, velocity of A is negative 1 meter per second. I'm going to actually plug this in. Negative 1. And the mass of A is still 3. Everyone comfortable? I just did 3 times 3 here. I probably should have plugged it in. Oh well. And then we're looking for velocity of B. And we know the mass of B is 3. Okay. Well, clean this up a bit more. We get 9 equals negative 3 plus velocity of B times 3. Okay, so we get 12 equals 3 velocity prime B. So velocity prime B equals 4 meters per second. So after that impact, the velocity of B would have been 4 meters per second. I did a lot of explanation here, but the key is really this. That the sum of the momentums before an impact equals the sum of the momentums after an impact. So we split it up like this and we plug in and we can figure stuff out. It really isn't hard at all. I'm going to do an example or two. This stays really easy even if we have different masses. So let's consider a situation where we have different masses. Maybe we've got 2 objects again. We'll just go with balls for now. A and B. Object A has a mass of 0.355 kilograms and a velocity of 0.095 meters per second. Okay. Object B has a mass of 0.710 kilograms and a velocity of 0.045 meters per second. I'm borrowing the numbers from page 185 of your book. I'm not borrowing the scenario, but the numbers are the same. That's where these numbers are coming from. Okay, so we got 2 objects, and object A, you see it's moving faster than object B, so it runs into object B and there's an impact. Okay, after the collision, so now we're down here, we still have A and B. This is after the collision. A is still going this way. This had a velocity already too. A is still going this way with the velocity, so that means this is a velocity prime of A with a velocity of 0.035 meters per second. We want to know how fast object B is going. All right? This shouldn't be hard. Why? Well, because, I'm going to move this up a bit. Because we know the right formula. And the right formula is PA plus PB equals P prime A plus P prime B, which we can further write as MA VA plus MB VB equals, I can't fit it, but this is just a continuation, MA V prime A plus MB V prime B. Fairly simple. So plugging into this, well, I should have written it over here. Oh well. I know the mass of A, which is 0.355, times the velocity of A to start with was 0.095, plus mass of B, 0.710, times the velocity of B, 0.045, equals, and I still don't have enough space, but we're good, equals the mass of A, which has not changed, it's still 0.355, times the velocity of A, well the new velocity of A, and it's in the same direction, so it's still positive, 0.035, plus the mass of B, which still hasn't changed, 0.710, times the velocity of B, which we don't know. Okay? This is ugly, but just be careful with your arithmetic and double check your calculations if you're using a calculator. This is fairly easy to solve and simplify, and we end up with 0.075 meters per second. Why? Because the momentum has to be conserved. The sum of the momentums before an impact has to be the same as the sum of the momentums after the impact.